So, today's topic is drape 3 friction spinning. Drape 2 we have already discussed, and now we are going to discuss drape 3 friction spinning. First, we will give a very short or brief description of the technology. What you see here is a simple line sketch of the two important parts of the machines. What we see here, that there are two drafting unit in this machine. You can say that this is a basically cross sectional view of the most important area of the machine, not the entire machine as such. It is basically kind of simple line diagram. So, there are two drafting units. In the drape 2 we have only one drafting unit, but in this case there is one drafting unit 1, which and there is another drafting unit 2. This drafting unit is more clearly shown in the right hand side of the diagram. So, there are two drafting units and there is a friction drum. In drape 2 also we have seen the friction drum is there. In this case basically there is one additional drafting unit that has been attached to the machines, that is drafting unit 1, that consists of basically a set of rollers. So, roller and apron drafting, which is here, and it is a single sliver feed, that we feed only one sliver through it, and then drafting is done at quite high speed, and the drafted fleece is introduced here in between the two friction drums. So, there are two friction drums as it is shown here, and the drafted fleece of fibers is introduced at the nip of these two friction drum, and whatever is fed by drafting unit 1, that becomes the core part of the final yarns. It goes into the core, and whatever is fed from drafting unit 2, that becomes the sheath part of the yarn. It has a core sheath type of structure. So, material fed through drafting unit 1 becomes core, and material fed through drafting unit 2 basically becomes your sheath. So, drafting unit 2, there are two opening rollers as you see it here, opening roller 1 and opening roller 2. These are the two opening rollers. The opening rollers rotate at a very high speed, we will see at what speed they run, and here we feed multiple slivers. So, this is the sliver feed here, not just one, we feed 5-6 slivers, whereas through drafting unit 1 we feed only one single sliver. And once the fibers are acted by the teeth of the opening roller, the fibers are sufficiently individualized, and then these fibers are directed towards the friction drum. So, for fibers to travel from the opening rollers to the friction drum, we need a support of air. So, there is a transport channel through which, or you can call it fiber feed duct. Through this duct, the fibers from the opening roller surface will be moving and ultimately will be landing on the friction drum surface. They are directed in such a way they land very close to the nip area of the friction drums. And the friction drum, which is shown it here in this side of the diagram, there are two friction drums, drum number 1 and drum number 2. The friction drum surface is perforated. So, there are lots of perforations on it, and then there are two suction insert here this this circle that you see, which is partially open over here, this is basically an insert inside the drum. So, on both sides of the drum we have two suction insert, and these inserts are connected to a suction pump. So, we draw air, and because the openings are only here in this zone and in this zone. So, here only the air can entry or the air can enter at the openings or where the slit actually exists, and therefore, this will cause the fibers to be directed at the nip of the two friction drums, and the drums rotate in the same directions. So, that at the nip area the two surfaces of the drums will move opposite to each other, but if we otherwise the drum rotational directions are exactly same. So, that is the direct basically description of the machine in simple terms, and if we want to understand the how the machine works, then as I said earlier, the drafted fleece from the drafting unit 1 will enter the nip zone of the two friction drum. So, here it is shown this is the nip zone, and a bundle of fibers which is existing here shown by the orange color. This bundle of fibers is actually the set of fibers which are being fed through drafting unit 1, and from drafting unit 2 thoroughly separated fibers, separated by whom? Separated by the opening roller. These separated fibers are made to move through the transport channel, and they also will come and actually land on the friction drum. And here in this diagram, this is shown, the green lines that you see here, these are the fibers coming from drafting unit 2, and the orange color indicates the fibers coming from drafting unit 1. So, two group of fibers are meeting. They are meeting where? They are meeting at the nip area of the friction drums. Now, as soon as the fibers from the drafting unit 1, that is this, are arriving at the nip zone of the two friction drums, two friction drum will act on that bundle of fibers. The bundle of fibers are pressed against the friction drum because the suction is acting. So, they are pressed, and now because the roller surface is moving, that is this roller is moving and this perforated drum friction drum is moving, and this perforated drum is also moving. As a result, at the zone where they are in contact with the two surfaces, the frictional force will work, like it is shown here by this blue line or blue arrow. So, both the surfaces of the friction drum will act on the group of fibers which are pressed against the drum surface, and because of the friction, the frictional force will act on them, which will generate torque, and as a result this bundle of fibers will be twisted. Now, this twist will be basically false twist in nature, because there is a continuity in the fiber supply from the front roller nip to the end of the drum within the drum. There is a continuous flow, it is not like open end spinning. The flow continuity exists, there is overlapping between the fiber. So, if the drum generate twist on these fibers, this twist is going to be false twist in nature. As soon as the fiber strand leave the drum surface or drum exit end, the false twist will be removed. Now, if the false twist is removed, obviously then there is no strength in the bundle. So, before the false twist is removed, therefore, we actually introduce fibers from drafting unit 2. These fibers will come, land on at the nape of the friction drums, and they will start wrapping around. It is shown here by the green lines. They will start wrapping around the false twisted yarn that exists between the drums. So, they will keep wrapping. So, now this entire structure consisting of the sheath fibers coming from drafting unit 2 and the fibers coming from drafting unit 1, all of them are going to move out from this twisting zone, and the sheath fibers which are wrapping the core, they will remain in wrapped state, and the core fibers which are false twisted, part of the false twist might get removed, but some false twists remain trapped in between, because the sheath fibers are actually wrapping over them. So, because sheath fibers are already started wrapping over them, even though the cores are trying to untwist, the entire twist which was present in the core, entire twist may not get removed completely, but that does not matter. So, sometimes we see in the structure of the yarn that sometimes the core part of the yarn has little bit of twist still left, though ideally we expect no twist with there, because the core is getting first twisted. But in the practical cases, some twist remains, because of by the time they are about to be removed, the sheath fibers are actually creating hindrance for the removal, and therefore, some twist remains trapped. That is what generally happens. Ultimately, what we get, a core sheath type of structure, core surrounded by a lot of sheath fibers. So, that is how the system is going to work, and as I shown here, the suction insert, and they are connected to the suctions. Suction also helps in the removal of dust and dirt. That is an additional advantage we get, because we are sucking at the yarn formation zone. So, if we process cotton, some dust particles are expected, they will be sucked. The yarn is withdrawn by a pair of rollers or withdrawal rollers, sometimes called take-off rollers, and the withdrawal speed varies between 100 to 300 meters per minute. So, the yarn is pulled out like it is shown here. These are the withdrawal rollers or take-off rollers. From there, the yarn goes to the winding unit, and you are all familiar with winding of yarn or cone or cheese. Construction and functions of machine components. So, we have already seen what are the main machine components. One is the drafting units. There are two drafting units. One of them is drafting by opening rollers, and the other one is drafting by roller drafting units. Fiber transport channel, twisting unit, withdrawal or take-up rollers, and then the winding unit. So, these are the basic components of the machine. Now, drafting unit 1 if we look at, you are already familiar with the drafting system. We have studied drafting system on draw frame, on roving frame, or ring spinning machines, and so many places. Roller drafting system, most of you have already studied. So, here also we have basically a roller drafting system, and we have 4 pair of rollers, because we have to give very high draft. Though we are not really spinning sliver to yarn in this case, sliver is drafted, we make it thinner, and that becomes part of the core basically. So, drafting units is basically 4/4 rollers with aprons. In the final zone we have aprons, because there the draft is more. The inlet speed of the first set of rollers can go up to 8.5 meters per minute. That means, the surface speed of these rollers, they can go up to 8.5 meters per minute, and typically the sliver which is fed here, usually it is little thinner in comparison to the sliver that we produce on carding machines or on draw frames. Generally 2.5 to 3.5 kilotex slivers are used, little finer slivers are used. The delivery speed of the drafting unit has to be slightly less than the delivery speed of the machine. So, this drafting, this is basically a high draft, high speed combinations. Delivery rates are quite high. It can, this delivery rate of the front rollers can go to the order of 150, 160, 200, 220 meters per minute. In comparison to ring spinning, if we see what is the delivery rate in ring spinning, hardly 15 or 18 meters per minute. So, it is almost 10 times more. So, all the rollers have to run very fast. So, the front rollers, if we fix the delivery rate 150 meters per minute or 180 meters per minute, so it runs very fast. And actually it can go up to 200 to 300 meters per minute. That is what is the claim by the machine manufacturers, but commercially generally people keep 180, 200, 250, 220, typically that is the speed. So, depending upon the kind of count we want to spin, the type of sliver and fibers we are processing, the right speed can be chosen. The upper and lower drafting rollers are connected to a suction unit to suck flies. That means, this part, this upper part from here to there, and the lower part, actually there is a suction system. Why? Because if the rollers run at a very high speed, a lot of dust, if it is we are processing cotton, lot of dust will be generated, and if not cotton also, lot of fiber flies will be there, because each and every roller running at a very high speed, they have their own air current, and these air current may be, there could be collision between the air currents of top and bottom rollers. As a result, there will be some disturbance to the flow of fibers, which leads to some fibers to move away from the main flow, and they become kind of fly, and we have to suck the fly immediately. Otherwise, these flies will be contaminate the surrounding atmosphere. So, therefore, we have to quickly suck them, and hence we need to have actual suction system there. The distance between the rollers, typical distance is shown here. The distance will depend upon the fiber length that we are going to process, and setting and draft combination, these have been already told in some other some other classes. So, the setting parameters, the exact draft distributions, they all depend upon the type of fiber we are going to process. So, typically here it could be 36 to 46, depending upon what fiber length we are going to process. So, this is the main draft zone and this is the pre-draft or break draft zone. We will also keep little bit of draft here just to keep the fibers under tension. The suctions unit may have ceramic guide for feeding an additional core in front of the high draft rollers. That is, here we can have a system of feeding the a filament, like in the diagram we are showing, that is the filament directly going into the nip of the front pair of rollers. See, advantage here is that we can have one more component as a part of the core, and that could be filament. So, for filament feeding, that could be some separate arrangement, but it is actually very simple. Filament bobbin is placed here and the filament is removed and actually fed at the nip. It has to finally go to the nip through some kind of guide eye. If I feed the filament here, then filament will be under stretched. So, that is, we cannot feed it here, we cannot feed it. So, this is not permitted, this is also not permitted, filament will be under tension. So, we have to feed the filament here only, so that it moves along with rest of the fibers and remain in this at the center part of the yarn. That is what is ideal. So, filaments are fed at the lower high draft rollers through filament feed arrangement. So, there are arrangements for feeding filaments. So, we can feed polyester filaments, we can feed nylon filaments, we can feed monofilament, we can feed multifilament, we can feed Kevlar, we can feed carbon fiber filaments. So, there are many options to feed different types of filaments and create a structure where you have filament staple fibers combinations. Drafting unit 2 is similar to what kind of drafting units we have in the case of rotor spinning machines, where the fibers from the slivers are separated by one opening roller. Here we have two opening rollers, 1 and 2, not just one. The two rollers are required because of complete separation individualization. We are actually feeding 5 to 6 slivers or 4 to 6 slivers are fed. Slivers individually are not very thick, they are 2.5 to 3.5 kilotex, and they are fed at a normally at a slow speed. The typical maximum speed is 1.2 meters per minute. So, comparison to the drafting unit 1, the sliver feed rate is much less, and we are feeding 4, 5 or 6 slivers together. And if we want to separate the fibers from the sliver, so what we do? First of all, there is a pair of drafting rollers with little draft. So, slivers are little drafted, and then they are moving towards the opening rollers. Opening rollers have their own teeth, and the way a sliver is opened in the case of rotor spinning, exactly same way it is done. The only difference is the one roller is not sufficient to individualize the fibers, and therefore, we have two opening rollers, and the opening roller speeds are very high, 12,000 RPM. So, as a result we get a very high individualization of fibers from the sliver. Now, the individualized fibers are made to pass through this transport channel. We will discuss about the transport channel. So, that means we have to remove the fibers from the teeth of the opening roller. The opening roller teeth geometry can also vary depending upon which type of fibers we are trying to process here, whether I am processing viscose rayon or processing or polyester fibers or nylon fibers or acrylic fiber, because you have lots of choices are there. So, depending upon the type of fibers and length of fibers, the denier of fibers, we want to process, the proper opening roller teeth or tooth geometry can be chosen. This unit is placed over the friction drum, just above the friction drum. See, the friction drums and the drafting unit 1, they are at the same plane, but the drafting unit 2 is placed above the 2 friction drums. If these are the friction drum, the unit is here, it is above, and the sheath fibers could be varied between 20 to 50% of the yarn mass. So, anything between 20 to 50% could be part of sheath, the rest is core. So, that kind of variation is possible. And transport or fiber channel is, so we have discussed about transport channel also in the while discussing rotor spinning as well. So, here also so many, there are more fibers have to be transported per unit time. So, transport channel is little larger, and this is the typical design of the transport channel, that it is divergent in nature. See, if you look at the from here to here the distance, let us say I write A and B, if I write C and D, so C D is larger than A B. So, it is like that only. But if you look at this side and this, it is narrowing down. So, channel is actually narrowing down from top to bottom. So, here whatever is the width at the bottom is little less. So, that the air velocity keeps on increasing from top to the bottom part of the transport channel, and this is also we required the tapering of the transport channel is going to increase the velocity of the fibers, which will help in straightening out the fibers, because the two ends of the same fibers will move at two different velocities. Any fiber, because fibers have a basically length dimensions, and hence the leading end and the trailing end of the same fiber will be moving at two different velocities depending upon where exactly they are located, and this little difference in velocity is going to straighten them out. That is the advantage we get by having tapered transport channel. But it has been also shown the divergent nature of the channel creates vortices, shown by this vortex gets created also, and because of this some of the fibers actually lose their straightened configuration. They can also get deformed because of the vortex which are generated. Now, the fibers are approaching the through the transport channel, it is they are moving or they are flying. Now, they are ultimately going to land on what? They are going to land on the friction drum. Now, friction drum surface speed is comparatively much less than the speed of the incoming fibers. So, the speed of incoming fibers are more than the surface speed of the friction drum. What is the result of that? Fibers after landing will be decelerated and they will get deformed. That is the situation that we have, that as a result of this fibers can get deformed, and actually many fibers get deformed because of this reason. And the speed of the fiber depends upon the flow rate and the shape of the channel, that is geometry of the channel and the properties of the fibers. Because ultimately, it is the air drag which is carrying the fibers. So, drag is a function of the diameter of the fiber, the cross sectional shape of the fiber, the length of the fiber, the surface roughness of the fiber. So, many aspects of the fiber also come into the picture. How the fiber is going to move, how quickly they are going to get accelerated as soon as they are released into the transport channel. Then come the twisting units. Twisting unit in our case or this case is basically friction drum. So, here is the simple sketch of the friction drum. Part of the drum surface almost 197 millimeter in length is having a lot of fine perforations. The total length is 242 mm and the surface of the drum is also knurled. So, that there is a friction, you have to have good friction between the drum surface and the fiber. So, the surface of drum is not really smooth, deliberately it has been made knurled surface, so that more friction can be there. Drum diameters are 45 mm, it is also shown here. Drum surface are perforated, because through those perforations actually the perforations are there. So, as they rotate and they reach the nip zone where the slit is there in the inserts, and through those slit the air is drawn, and therefore, the air will be able to pass through the perforations of the friction drum. Therefore, the entire surface is having perforations. They have special nickel diamond coating in order to reduce the wear and tear. Drum speed varies between 3000 to 5000 rpm, that is the typical speed range of the friction drum. And the speed of the rear drum is 10% lower than the front drum. These two speeds are not exactly same. Suppose N1 is the front drum, then N2 speed is little less than it, around 0.9 N1, and this is done why? The lower speed of one of the drum ensures gradual tightening of the sheath fibers wrapping around the core. That is the reason why there is little difference in the speed of the two drums. The wrapping fiber, the sheath fibers, as they start getting wrapped, this wrapping action is going to be gradually they will be tightened. If one drum moves slower than the other, and this tightening will help in enhancing the yarn strength. Number of perforated rows is around 88, spacing between the drums 0.2 mm or sometimes 0.1 mm also. The number of holes in a row per row is 104, total number of perforations is 9152 on the entire surface of the drum. So many perforations are there. Delivery unit is consist of, as it is shown here, 3 rollers are there, and there are 2 nip zone. This is going to help to pull the yarn at a very we have to pull the yarn at a very faster rate. No, the delivery rate is 180 or 200 or 250 meters per minute. So, just having 2 rollers grip on a yarn is not sufficient to pull the yarn at a very high speed. There is a possibility of slippage. To avoid that, we will have a 3 roller system where there are a nip zone over here, another nip over here. The yarn is actually gripped at 2 points and then they are pulled out. So, that to avoid the slippage. And the take up roller surface speed is usually 3% greater than the speed of the front roller. so that the yarn remains under little tension. So, shutter speed is usually 3%, sorry, the take up roller speed is 3% greater, yes. If it is more than the delivery roller of the drafting unit 1, then the yarn which is there and getting formed between the drums, it will be remaining under tension. We have to apply some tensions, and hence there little, we can say there is a tension draft of 1.03. And the winding unit is a typical, actually exactly similar to the winding units that you have already studied. The bobbin traverse could be 150 to 200 millimeter, maximum bobbin diameter could be 400 millimeter. Between take up roller and winding drum, there are deflection rollers which even out yarn tensions. So, there are some deflecting yarn path which is created in order to even out the tension variation in the yarn when the yarn is going to be wound on the winding drum. And the winding zone yarn tensions also can be changed or can be regulated. That means, the take up roller speed and the drum surface speed, there is a difference between these two. Drum surface speed little bit more, so that there is a tension in the yarn, and whatever tension, that tension can be controlled, so that we can get a package of right density. Otherwise, the package may be very soft or may be very hard. So, we have some control on the tension in the yarn at the winding zone, and accordingly we will be able to build a package of right density. For coarser count, a higher tension is maintained than finer count. Here is the specification of the friction spinning machine, drape 2 and drape 3. Spinning positions could be like this. We can get a machine with 6 or 12 or 24 or 48 positions. For drape 3, it can go up to 96 positions. Delivery rates are also stated here, the kind of fibers it can process. See, here we have fibers in the case of drape 3, Kevlar, Nomex, carbon, they can be there and they can be put into the core. Or sheath, we can have cotton, man-made fibers or blends. So, we can feed the fibers through drafting unit 2, which are going to form the sheath. So, here we can have a combination fiber, 2 fibers of cotton, 3 fibers of polyester or some other fiber, whatever combination we want, we can have the fibers there, or we can pre-blend the fibers and make fibers and then feed them also. So, you have many options to play with the structure of the yarn or play with the placement of fibers within the yarn cross sections. That advantage we have in this kind of spinning system. Therefore, this spinning system is very suitable for technical yarns. And generally, the count range, if you look at it, is very coarse. So, drape 2 yarn can never be used for apparels, because it is suitable for only coarse count. For drape 3 yarns, we can go up to 18 any also, but generally this is also used mostly for producing technical yarns. And other specifications are stated here. Now, we are going to discuss setting of yarn count, that is how to set a particular count of yarn that we want to produce. Let M1 is the count of feed fibers in drafting unit 1. So, there are 2 drafting units. So, from drafting unit 1, let us say the count of feed fiber is M1, M2 is the count of feed fiber in drafting unit 2, which is going to form sheath fibers. My is the count of yarn in tex. So, tex basically means milligram per meter, you have to remember, and kilotex means gram per meter. V1 is the velocity of the feed sliver in drafting unit 1 and V2 is the velocity of feed sliver in drafting unit 2. Vy is the velocity of yarn take up, that is, or yarn withdrawal. N1 is the number of core slivers, usually it is 1, and N2 is the number of sheath slivers, it could be 4, 5, 6 like that. X1 is the percentage core and X2 is the percentage of sheath. For mass balance at steady state operation, one can expect whatever we feed, the same amount should be delivered. So, input from drafting unit 1 per minute plus input from drafting unit 2 per minute, that becomes my total input, that should be equal to delivery of the yarn per minute. So, here delivery basically means not in terms of how much length it has delivered, but how much weight of yarn it has delivered. So, mass balance is basically you are discussing about the mass or the weight of fiber being fed and weight of fiber being delivered. So, there are two channels through which the fibers are being fed and there is only one channel through which the fibers are taken out in the form of yarn. So, therefore, we can write the simple equations. Input from drafting unit 1 per minute is going to be this, input from drafting unit 2 is going to be this, and the delivery of the yarn is going to be this. So, we write M1 V1 plus N2 M2 M2 V2 equal to My 10 to the power minus 3 into Vy. Why 10 to the power minus 3? Why it is 10 to the power minus 3? That is because My is what? Is the text value of the yarn. So, text value of the yarn basically means it is milligram per meter, whereas M1 which is the kilotex value of the sliver. So, it is gram per meter. So, it is gram per meter into velocity means so much of gram I am feeding. This is also gram per meter into delivery speed into so many slivers being fed. It is giving me total gram being fed per minute. So, I have to on the right hand side you have to also have the same unit. So, you have to go for gram unit. So, milligram per meter should be converted to gram. So, we have to divide it by 1000. That is why it is 10 to the power minus 3. So, My divided by 1000, we write it My into 10 to the power minus 3, it becomes gram per meter into Vy, that is the speed with which we are delivering. So, so much gram of fiber being delivered and so much gram of fiber from here to there, so much gram of fiber per minute I am feeding, and from here to there is so much gram of fiber we are delivering. So, they are same. With this, if let us say x1 is the percentage core, then we can write the core delivery which is M1 V1, whatever is being fed from drafting unit 1, that is going to be basically My into the power minus 3 into Vy into x1 by 100. This is the percentage of core which is present in the yarn. So, this is the total is yarn mass out of that x1 percentage of the yarn is forming core. So, m1 v1 should be equal to this. So, from there we can write what should be my delivery rate, that is v1. So, from here we find out what should be the v1. So, straight away we come to v1, m1 goes on the right hand side. So, it will go at the denominator. Similarly, we do it for the sheath percentage also, and we can say that V2 is going to be exactly same way, only x1 will be changed to x2, or x2 is the percentage of sheath. So, x1 by 100, it will be x2 by 100, and the equation remains fairly basically same. So, that way we can find out the feed rate at the drafting unit 1 and feed rate at drafting unit 2. So, when we want to set the machine, then we have to actually most of the time we have to adjust the feed rate. So, now we will solve a problem and that will make it clear. Problem number 1 or example 1. A 100x yarn is to be produced. The core and sheath fiber linear densities are 3.5 and 3 kilotex respectively. Number of sheath fibers to be fed is 6. The feed rate of core and sheath fibers are 1.5 and 0.8 meters per minute. We have to calculate the yarn delivery rate and the core and sheath percentage in the yarn. So, how to go about? My, this is the mass of yarn, is 100 tex, that means 100 milligram per meter. M1 is 3.5 kilotex, that is 3.5 gram per meter. M2 is 3 kilotex, 3 gram per meter. V1 is 1.5 meters per minute. V2 is also given 0.8 meters per minute. N2 is also given 6. So, first of all, we write all those parameters whose values are given. Now, we have to make use basically of the mass balance equations. So, we know that M1 V1 plus N2 M2 V2 equal to this, we have seen it earlier. Here we simply substitute the values. If we substitute the values, what is missing here is actually in this equation Vy. We need to find out the yarn delivery rate, that is Vy. So, straight away we will get the value of Vy. Yarn delivery rate will come 196.5 meters per minute. No, this will be multiplied by 10. And it will be 196.5. It is not divided, it should be multiplied. So, 19.65 is this side, multiplied by 10 will give you 196.5 meters per minute, that is the delivery rate. We need to calculate that in this situation what is going to be the core percentage and sheath percentage. So, if we know this equation V1 is this, and therefore, from here we can write x1 will be m1 v1 into 100 divided by my 10 to the power minus 3 into Vy. So, now is a question of basically substitution again, because the values of the different parameters are already stated. What was earlier not known is Vy. So, Vy you have found out in the previous section, and that Vy value we are going to now place it here, that is 196.5. And if we do it, we get a figure 26.71. So, the core percentage is going to be 26.71, and exactly same way we will calculate the sheath percentage, which is x2, and similarly we substitute the values. Only V1 Vy values were not known earlier. We whatever value of Vy you have found out, same values we are putting it, that is 196.5, that is the delivery rate, and we get a figure now 73.28. That means, our core will be 26.7% and sheath will be roughly 73.3%, let us say approximately. And if I add these two, this plus this, they must be 100. So, if we add this and this figure is 99.99. So, it is almost close to 100. That means, the answers are correct. So, this is how we can find out the core percentage and what delivered, what under this condition what should be the, what would be the core and sheath percentages, and how much delivery rate we have to keep on the machine, so that the machine keeps on producing that 100 takes yarn. We will take another example. What is this example now? Example number 2. Read the example. 150 takes yarn is to be produced with core sheath ratio 70:30. The count of sliver meant for core, that is cotton, and sheath polyesters are 3.5 kilotex and 4 kilotex respectively. So, the sliver that we are going to use for core and sheath, their kilotex values are given. The number of polyester slivers to be fed is 5. That is the decision we have taken, that we feed 5 slivers. If the yarn delivery rate has to be 150 meters per minute, what should be the feed rate of cotton and polyester slivers in this case? What should be the feed rate of cotton and polyester slivers? Because accordingly, we will adjust the feed rate and of both cotton slivers and polyester sliver. So, for a given core sheath ratio, some parameters are already known. We need to find out what should be the feed rate of the cotton and polyester slivers, because once you want to work on the machine, this is what you need to do. First, note down the values which have been given already. So, 150 tex yarn means 150 milligram per meter. M1 is 3.5 kilotex, V1 is unknown. So, V1 there is a question mark. M2 is also given 4 kilotex, that is 4 gram per meter, but V2 is unknown, we need to find out. M2 is given, how many slivers will be feeding in drafting unit 2, that number is 5. And the yarn has delivery rate from commercial point of view has been decided to be 180 meters per minute. So, if it is 180 meters per minute, I think we have to make a correction here. This should be 180 meters per minute. There could be some typing error sometimes. So, you have to understand the typing errors. So, V y is 180 meters per minute, that means the delivery rate has to be 180 meters per minute. So, we can find out now V 1. V 1 formula has been given earlier. If one can remember, it is fine. If you do not remember, even then it is okay. You have to go for, you have to think the logic. Logic is mass balance. How much quantity of fiber I am feeding, that must be equal to the quantity of fibers I am delivering. So, you need not to think in terms of yarn or sliver, just think there are two channels through which fibers are fed, and there is one channel through which fibers are delivered. So, how much fibers I am feeding and how much fibers I am delivering, they should be equal. And if you remember this logic, you can apply this and also can find out the value of V 1 and V 2, because with the same logic we have found out the formula for V 1 and formula for V 2. If V 1 is this, so we just substitute the values, we get a figure 5.4 meters per minute. And V 2, similar formula, you use the values here, we get 0.405 meters per minute. That means, in this case the polyester slivers which are going to form the sheath is fed at a very slow rate, because 5 of them are being fed. So, their feed rate is 0.405 meters per minute, whereas the cotton sliver which will go inside, that is, that will go into the core, that is fed relatively faster rate, because I am feeding only one single sliver. So, I have to feed it faster. So, V 1 is therefore always more than V 2, and the machine manufacturers has given this provision. So, that V 1 can be adjusted over a larger range in comparison to V 2, because while designing the machines, designing the drive, these aspects have to be kept in mind. Accordingly, the drive has to be designed. Generally, we have to know what type of counts of yarns we are going to produce, what could be the possible core sheath ratios, extreme values you have to take, and accordingly then you have to back calculate to find out what should be the feed rate in drafting unit 1, what should be the feed rate in drafting unit 2. So, if these are the feed rates which we require, now one has to design the drive and keep this flexibility, so that the feed rate of drafting unit 1 can be changed within this range, or drafting unit 2 can be changed within this range. So, accordingly actually the designing is done. So, before that actually all these calculations are done, and then only the drive design actually starts, where one has to find out the gear train, or if it is driven by motors, then what should be the speed of the motors, how the speed of the motors can be controlled, and in which range we should control it. So, with this part of this lecture is over now, and next we will go to the, I think we will have 1 or 2 more lectures on the friction spinning. we will study the yarn formation mechanism, we will study the structure part of the yarns and some process parameters, how they affect the yarn quality or processing efficiency, and what could be the applications of such yarns. So, these are the things we are still left, we will cover in the coming lectures. Thank you.